Here in this figure, a boiler cell is shown to you, which is used to store steam at a very high pressure. So there are two kind of joints. One is called the longitudinal and other is called the circumferential joint. So this joint, which is along the length of the shell, is called the longitudinal joint, and which is along the circumferential direction, it is called the circumferential joint. So here what is happening in this case, the boiler plate is bent in the form of a ring, and these two ends are joined together with the help of the butt joint. Okay. So this is a double strap butt joint because we use two cover plate here, one on the upper side and other on the lower side. And on the one side we have the two rows of rivet, and on the other side again we have two rows of rivet. So this is called the double riveted double strap but longitudinal butt joint basically. And here in this, see, this joint which is along the circumferential direction is called the circumferential boiler joint, and this is used to join two boiler cells together and to increase the length of the boiler cell. Basically here one shell is overlapped to the other cell, and with the help of this circumferential joint we can make a connection between these two cells basically. Let us understand how to design these joints in this video. Here in this slide we understand how to design the longitudinal boiler joint. As we see in the previous class, this the boiler plate is bent in the form of a ring, and there are two ends, and these two ends are joined together with the help of the butt joint. So this is the arrangement of the butt joint here, and there are two cover plate. One is shown by the green color. This is called the outer cover plate whose thickness is T1, and this pink color plate which is at the inner side is called the inner cover plate whose thickness is also T1 basically. And we see that on the one side there are three rivets, and on the other side there are three rows of rivet. So this joint is normally we call as a triple riveted double strap butt joint basically, because there are three rows of rivet on one side and three rows of rivet on the other side, and there are two cover plate. That's why this is called as a triple riveted double strap or double cover butt joint basically. Now let us see how to first of all see the arrangement of this one, and the thickness of the plate is normally we call as a T here. Now we see that there are three rows of rivet here. One is called the upper one is called the outer row of rivet. Inside this we have an inner row of rivet, and the third row of rivet we also call the inner one. This middle one normally sometimes we call it as a middle row, and this is the inner one basically. The arrangement of the rivet is shown here. This is a zigzag riveting arrangement of the rivets here. The pitch of the outermost row of the rivet is supposed to be P. The pitch is normally defined as the distance between center of one rivet to the center of the other rivet in the same row basically. Okay, and the pitch of this middle row or the inner row is half of the pitch of the outer row basically. So here the distance between center to center distance of the row of these rivets are P by 2 in the first inner row basically, or we call them as a middle row, and also in the inner row basically. Now the distance between the two row of rivet is called the transverse pitch. So this is called PT here, this is called PT, and this margin normally we call as the distance of the outermost of rivet with the edge of the plate. So here we have, this is the edge of the plate and this is the row of rivet. The distance between them is called the margin of the plate basically. So, and the diameter of the rivet here is dr. So let us understand how to find out all the parameters step by step. The first step is to find out the boiler cell thickness, T. So here in this figure a boiler cell is shown to you, and the inside diameter of this boiler cell is ds, or sometimes it is denoting by the symbol di. This boiler cell stored steam at pressure P. Sometimes this symbol is called as Pi. When this high pressure steam is stored inside this boiler cell, so because of this steam pressure there should be chances that this boiler cell will burst into two halves. So this is the upper half and this is the lower half, and this area which is shown by the shaded lines, and this area will offer some resistance to this type of failure basically. So when this area offers some resistance, so some stresses are developing across this cross section or across this area, and this stress is denoting by the symbol sigma T, that is normally we called as hoop stress. The thickness of the boiler cell is T and the length of this boiler cell is L. So this area offers some resistance. This is the left side area and this is the right side area. Both the area will offer some resistance. So we have to equate the force which are exerted by this steam pressure P, and we have to equate this force with the force which is, or the resistance which is offered by this material. So P into ds into L, P is the pressure and this is the area, ds into L is the projected area, okay, because ds is the diameter of this one and L is the length of this one. So ds into L is the area and multiplied by P. So this is the force which are exerted by the steam pressure, and that should be equal to sigma T into 2TL. Sigma T is the hoop stresses into area is 2TL, because the TL is the area on the left side and TL is the area on the right side. So this is twice TL. So from this expression we find the value of T, that T should be equal to P ds divided by 2 sigma T. Sometime in this formula, this P is written as Pi and this ds is written as Di basically. So whenever the efficiency of the joint is given to us, then T should be equal to P ds divided by 2 sigma T into efficiency. Now the boiler cell thickness, we use this formula, T should be equal to P ds divided by 2 sigma T into efficiency plus corrosion allowance. What is happening, because when the steam is stored inside this boiler cell, what is happening, because of this steam, there should be chances that this internal surface will be corroded, and to compensate for this corrosion, some allowance we have to add, and to that allowance we are called as a corrosion allowance. The value of this corrosion allowance is 1.5 to 2 mm. So between these two values, between the range of 1.5 to 2 mm, we can put any value of the corrosion allowance. As far as this stress is concerned, hoop stress is concerned, this should be equal to ultimate stress divided by factor of safety. The factor of safety for the boiler cell is in the range of 4.5 to 4.75. Normally we take this value as 5. As far as the material of the boiler is concerned, normally two grade of steels are used, that is ST37BR and ST42BR, and the value of the ultimate tensile stress is given in the range of 360 to 440 megapascal and 410 to 500 megapascal. Now as far as the efficiency of the joint is concerned, with the help of this table we can find out the efficiency depending upon the type of the joint and depending upon the rivet arrangement. Suppose we are using a double strap butt joint and we are using a single rivet, then the efficiency is in the range of 55 to 60%. If we are using a triple riveted and double strap butt joint, the efficiency is in the range of 80 to 90%. If we are using a lap joint, so the efficiency should be, for the single rivet, it should be 45 to 60%. So depending upon this type of the joint and depending upon the type of the rivet, number of rivet, basically we can decide the efficiency, and we put this value in of efficiency, stress, okay, and the diameter and the pressure here, and we add the corrosion allowance here, and with the help of this formula we got the value of the thickness of the boiler cell. The next is to find out the diameter of the rivet and the diameter of the hole. So diameter of the rivet normally we call as dr, and this can be found with the help of the Unwin formula. So the first thing is, if the thickness is more than 8 mm, so diameter of the rivet should be equal to 6 under root T, where T is the thickness in mm. So the results we got, or the dr we got from this formula, is in mm also. If the thickness is less than 8 mm, so we equate the shearing resistance of the rivet with the crushing resistance, and with equating these two resistance, shearing resistance with crushing resistance, we find out the diameter of the rivet. And in no case, the third is, in no case the diameter of the rivet should not be less than the thickness of the plate. So next is the diameter of the rivet hole is always more than the diameter of the rivet basically. So what we do, we add 1 to 2 mm in the diameter of the rivet, we got the diameter of the hole by using this formula. Next, let us see how to find out the pitch of the rivet system. So the pitch of the rivet is normally obtained by equating the shearing strength with the tensile strength. So the tensile strength at the outermost of the rivet is normally P minus dr into T into sigma T, where sigma T is the stress, and this P minus dr into T is called as the tensile resisting area basically. Now let us see how to got this value. So this is the tensile strength per pitch length. So we see that how many number of rivet lie in the per pitch length in the outermost row. So the pitch is defined as normally the center to center distance of the rivet in one row basically. So this is pitch, and in this pitch P, the half rivet lies on this left hand and the half rivet lie on the right side basically. So there are one complete rivet which lies in the per pitch length here. So the net effective area of the plate, because there are two holes here, so this net effective area, this distance normally we call as a P minus D into thickness of the plate is T here. So this is P minus dr is the diameter of the rivet into T into sigma T. So this is the tensile strength of the rivet basically in the outermost row, and we equate with the shearing resistance. So shearing resistance is given by this formula. So this is the shearing resistance because of the rivet which are filling in shingles here, and this is the shearing strength of the rivets which are failing in double shear. So there are two numbers, one is called the N1, other is called the N2. Basically N1 is the number of rivets which are failing in single shear, and N2 is the number of rivets which are failing in double shear. Let us understand how to find out this value of N1 and N2. So we have to understand this arrangement here. If we see that there are 3 rows of rivet basically inside this butt joint, and there are 2 cover plate of unequal width. So if you see this the rivets of this outer row, so there are only 1 cover plate, and that is inner strap cover plate. So this outermost rivet, they will fail only in single shear. Okay, and this value is normally we called as N1. N1 is the number of rivet which are failing in single shear. So in this, for this type of arrangement, for the given arrangement, basically we say that the outer row of rivets are failing in single shear. So we have to find out the number of rivets per pitch length. So with the numerical problem we understand this. Next is the value of the N2 is the number of rivets which are failing in double shear. If we see that the inner there are 2 inner rows, this is the first row, this is the second row basically. So these 2 inner row rivets having 2 cover plate, one on the upper side which is shown by the green color, and other on the blue side on the inner side which is normally shown by the pink color, and in between we have the plates and we have the rivets. So when there should be chances of the shearing failure of these inner row rivet, they will fail in single and double shear basically, because there are 2 cover plate and between we have the plate. So this is the value of N2. N2 is the number of rivets which are failing in double shear per pitch length basically. So the the rivets of the inner rows are failing in double shear. Okay, so this way we can find out the value of N2. Okay, and here instead of taking 2, the boiler regulation says it is taken as 1.875. This pi by 4 d square into tau is the shearing resistance of the rivets which are, and if you multiply this by N1, so we got a single shear. This is instead of 2 we have taken 1.875, and pi by 4 d square into tau is again the shearing resistance of the, and multiplied by N2 of the rivets which are failing in and double shear basically. So by equating these two values we can get the value of P. P should be come out to be N1 plus 1.875 N2, close the bracket, pi dr square tau divided by 4t into sigma t plus dr. With the help of this formula we put all the values and we got the value of the pitch of the rivet basically. Now there should be some, you can say, a restriction or some limitation on the pitch basically. The pitch should not be less than the P minimum, and it should not be more than the P maximum value. So P minimum value should be equal to twice times of dr, where dr is the diameter of the rivet, and P maximum pitch should not be it should be equal to KT plus 41.28, where K is the constant and T is the thickness of the plate. So this K we can get with the help of this table, with the depending upon the type of the joints and depending upon the number of rivets per pitch length. Okay, suppose we are using a double strap butt joint and the per pitch length the number of rivets are 3, so we use the value of 4.63. So we put the value of K here 4.63. So with this formula we got the value of P maximum, and with this one we got the value of P minimum. If this value of the P lies between P minimum and P maximum, so we accept this value of the pitch whatever we got from the formula. If this P value is less than the P minimum value, so we accept P minimum as the pitch of the rivet system. If this P value is more than the P maximum value, then this P maximum value we assume as the pitch of the rivet system. If this P value lies between P minimum and P maximum, so whatever value with this formula we got, we take this value as a pitch of the rivet system. Now let us understand how to find out the transverse pitch. So transverse pitch is represented by the symbol PT, and let us understand this. What is the meaning of this one? So we see that there are 3 rows of rivet in this present case, and this is the outer row, this is the first inner row, and this is the second inner row, and the distance between these rows of rivet normally we call as a transverse pitch, which is represented by the symbol PT. So the distance between the outer row and the first inner row is called PT, that is called transverse pitch, and the distance between the first inner row and the second inner row is also called the transverse pitch. Let us understand the concept of number of rows of rivet in each row basically. So in the outer row, if we see, there is only 1 rivet per pitch length, because in the per pitch length half rivet on this side and half rivet on this side, so half and half is equal to 1 basically. So in the outer row there is 1 rivet per pitch length. If we come to the inner row, in the same pitch length P, we have that between these two lines there are 2 rivets here. So in the first inner row there are 2 rivets per pitch length. Also in the second inner row, there's half rivet on this side, half on this side, there's half of 1 and 1, 2. So again in the second inner row there are 2 rivets basically. So we see that in each and every rivets or the number of rivets in the outer row is different from the number of rivets in the inner row, because outer row having only one rivet and the both the inner rows having only two rivets basically. So here the first case is equal rivets in each row. So we see with this example that there are unequal rivets in each row basically. So when there are equal rivets in each row, so we use the formula PT should be equal to 0.33p plus 0.67 into dr for zigzag riveting, and PT should be equal to twice times dr for chain riveting. Okay. Now when we understand the second case, when the number of rivets in the outer row is half the number of rivets in the each inner row, so which is the case here basically. In the outer row we see there is one rivet, and in the inner row there are two rivets. So in the outer row the number of rivets are half as compared to the inner row of rivets basically. So this is the case here. And when the inner rows are zigzag riveted, so we see here that the inner rows, the arrangement of the rivets are not identical to the outer row, so normally we call them as zigzag riveting. So when there are zigzag riveting, then the PT should be equal to 0.2p plus 1.15 dr for outer row and the next inner row. Okay, so this is the outer row and this is the first inner row or the next inner row, and this distance PT is normally will given by this first equation. That is PT should be equal to 0.2p plus 1.15 dr. Okay, so this is the transverse pitch for outer row as well as for the first inner row. Okay, and the PT should be equal to 0.165p plus 0.67 dr when rows in which full number of rivets lies, means the distance between the first inner row and the distance between the second inner row, and this distance is found out with the help of this equation basically. So in this we have understand how to find out the transverse pitch. So let us see how to find out the margin and thickness of the strap. So margin is normally taken as 1.5 dr to avoid the tearing failure of the plate at the end. So in most of the cases we take m should be equal to 1.5 dr. The thickness of the strap where every alternate rivet in the outer row is omitted, and when there are unequal width strap, so T1 should be equal to 0.75 T for wider strap and T1 should be equal to 0.625 T for narrow strap. So here we see in the present case there are two strap plate. One is the outer strap plate which is shown by the green color, and there is one inner strap plate which is shown by the pink color basically. And we see that the width of this outer strap plate is shorter than the width of the inner strap plate. So this outer strap we can say is the narrow one, and this inner strap is we can say is a wider strap. So when we see that when these two strap plates are used in this case, and both the strap plates are of unequal width, so T1 is finding out with the help of this formula for wider strap, and T1 should be equal to 0.625 T for the narrower strap. When we use the equal width strap, so T1 is same for both the strap plate, and T1 should be equal to 0.625 T in bracket P minus dr divided by P minus 2 into dr, so it's a bracket. And we see that in no case the thickness of this strap should be less than 10 mm. So let us understand the whole procedure of designing of the longitudinal butt joint with the help of an example. So in this example we have to design a triple riveted double strap longitudinal butt joint, and the strap plates are unequal in width. So the data given in the problem is the diameter of the sail is 0.8 meter, the pressure of the steam stored inside this sail is 2 megapascal. The pitch outer should be equal to twice times pitch inner rows, so the outer row rivet is twice times the pitch of the inner rows here. The zigzag pattern means the rivets are arranged in the zigzag pattern, and the efficiency of the joint is 80%. The tensile stress is 80 megapascal, the shear stress is 60 megapascal, and the crushing stress is 120 megapascal for the material of the rivet basically. So as per the design procedure, first we have to find out the sail thickness. The sail thickness is given as T equal to PDS divided by 2 sigma T into efficiency plus corrosion allowance, where P is the pressure, okay, DS is the diameter of the shell, the sigma T is the hoop stress or the tensile stress for the given material, and this is the efficiency of the joint. So we put here P is equal to 2, this DS is the diameter of the sail is, that is 0.8 meter. We convert this diameter into mm, so we multiply this diameter by 1000, so this is 0.8 into 1000 divided by 2 into sigma T stress is 80 megapascal. We put this value of stress 80 megapascal here. Then we put the value of the efficiency of the joint, that is 80% means 0.8. So we put the value of 0.8 it has an efficiency of the joint. As per the corrosion allowance is concerned, we add here the value 2 here, that is 2 is in mm. When we solve this expression, we got 12.5 plus 2, that is 14.5. We can round off this value to 15 mm. So we got, with this formula, we got the value of cell thickness as 15 mm. This cell thickness is more than 8 mm, so we use the unwind formula to find out the rivet diameter. So the rivet diameter is dr should be equal to 6 under root t. 6 under root t, the value of t is 15 in mm, so we can get this value as 23.23. so we can round off this value to 24 mm. So when we put the value of t here in mm, we got the diameter of the rivet in mm. Now we have to understand how to find out the value of the pitch in the outer row, that is defined as pitch. So there are 3 rows of rivet. This is the outer row, this is the first inner row, and this is the second inner row. The distance between the 2 consecutive rivets is normally we called as a pitch, that is defined as P here. So this P is found out using the formula, that is inside the bracket n1 plus 1.875 n2 into pi dr square tau divided by 4t sigma t plus dr, where dr is the diameter of the rivet, tau is the shear stress, t is the thickness of the cell, and sigma t is the tensile stress, plus dr is the diameter of the rivet, where n1 and n2 are the number of rivets which are failing in single shear and which are failing in double shear. So let us see how to find out this value of n1 and n2 here. So let us see this arrangement here. So here we see that there are this blue color part is normally we called as a cell whose thickness is t, and there are 3 rows of rivet, okay? And we see that there are 2 cover plate which are of unequal width, that is outer cover plate, and this is the inner cover plate. This outer cover plate is shown by the green color lines, and this inner cover plate is shown by the pink color line. The thickness of the outer cover plate is T1 and the thickness of the inner cover plate is also T1 here. Now we see that the rivets in the outer row, okay, they are only having one strap plate, that is inner strap plate, and there is a shell over it, okay? So there is a shell and there is a inner strap plate, and we join these two with the help of this rivet joint here. So this rivet which are in the outer row, it fail in single shear. Now let us see what is the value of this n1 here, okay, number of rivets per pitch length. So this is the outer row, and in the outer row we see that per pitch length there is only one rivet, half on this side and half on this side, okay? So the value of n1 is 1 here, okay? This is the number of rivets which are failing in single shear. So here we see that outermost rivet, or the rivet in the outer row, is normally failing in the single shear, and this per pitch length is equal to 1 here. Now this value of n2 is the number of rivets which are failing in double shear, okay? So we see that here the inner row of rivet, they have 2 cover plate, one is on the top and on the bottom basically, and between we have the cell whose thickness should be equal to t. So there are 2 plates, one on the upper side, other on the lower side, okay, and they are joined with the help of the rivets here. So the rivets in the inner row, they are filling in double shear, okay? So the rivet in the first inner row and the rivet in the second inner row, these rivets are filling in double shear. So let us see how much is the value of n2 here. So n2 is the number of rivets per pitch length. In the per pitch length P, there are 2 rivets which are lie in the first inner row, and there are 2 rivets which lie in the second inner row. This is the half rivet on this side, half rivet on this side, and 1 rivet in the below. So there are total 4 number of rivets which lie per pitch length in the inner row, which are filling in double shear basically. So this value of n2 here is 4. So we put the value of n11, n2 is equal to 4, and put all the value here. We put the value of t as 15, we put the value of sigma t as 80, we put the shear stress as 60, and when we solve this expression, we got the value of 216 mm. So from the formula, we got the value of pitch as 216 mm. We have to check that this value should lie within the pitch minimum value and the pitch maximum value. So we find this value, the P minimum value should be equal to 2 into dr, that is 2 into 24 should be equal to 48 mm. So this satisfies this criteria. This value of pitch is more than this value, that's okay, but we have to compare this P value with the P maximum value. So P maximum value should be equal to K into T plus 41.28. So K is a constant whose value is T for this given arrangement, because there are 2 step plates of unequal width and there are 3 rows of rivet. From the table we find this value of K. The value of K come out to be 6 here, into T is 15 into 41.2. This value is coming out to be 131.28 mm basically. So we see that this P value is more than the P maximum value, because P value is 216 and the P maximum value is 131.28 mm. But we know that this pitch value should lie between the value P minimum and P maximum. So we say that this maximum pitch is the pitch of for the given arrangement. So this P maximum should be 131.28 mm. So we know that this pitch will be lie between the value P minimum between the value 48 to 131.28 mm. It should not be more than this P maximum value. So we can round off this number to the nearest lower number, and the nearest lower number we taken as a 130 mm basically. Okay, so this 130 mm lie between this P minimum value and the P maximum value. Now we have to find the value of the transverse pitch. This PT is called the transverse pitch here. The transverse pitch is normally defined as the distance between the rows of rivet. This is the outer row, this is the first inner row, and this is the second inner row. The distance between these row of rivets normally we call as a transverse pitch. So the transverse pitch between the outer row and this middle row or the first inner row, that is PT, is found with the help of this formula. That is PT should be equal to 0.2p plus 1.15 dr. We put all the value here. We put the value of P as 130, we put the value of dr as 24, we got this value of 53.6 mm. We can round off this value to 55 mm. Now the transverse pitch between the middle and the inner row, so this is the middle row or the first inner row, and this is the second inner row, and the distance between them is also called the transverse pitch. So this transverse pitch can be obtained by using this formula, that is 0.165p plus 0.67 into dr. So we put the value of P here 130, we put the value of dr here 24, and we got this value as 37.53. We can round off this value to 40 mm basically. Now we have to find out the thickness of the inner strap plate and thickness of the outer strap plate here. So in this formula, in this arrangement, we will see that there are two strap plates which are of unequal width. This is called the outer strap plate, which is the narrower one, and we have the inner strap plate, okay, which is the wider one basically. So, and they are of unequal width. So for unequal width strap plate, there are two formula. So thickness of the inner strap plate, which is wider one, as 0.75 t. We put the value of t here as 15. We got this value of 11.25. We can round off this value to 12 mm. Now the thickness of the T1 of the outer strap plate, this is the outer strap plate basically. The formula is 0.625 t plus 0.625 into, we put the value of t here as 15. That is coming out to be 9.38 mm. So we can round off those to 10 mm. So this is the outer strap, which is the narrower one, and this is the inner strap, which is the broader one. Next we have to see how to find out the efficiency of the joint. So next we have to find the value of the efficiency of the joint. So efficiency of the joint is normally defined as the least of the PT, PS, PC divided by P solid into 100 here. So let us see how to find out these different values here. So the PT is called as tensile strength per pitch length. So this is P minus dr into T into sigma T here. We put all these values in this equation and we got this value. This PT value come out to be 127.22 kilonewton. The shear strength per pitch length we have to find out. So we have to find out the number of rivets which are failing in singles here, and the rivets which are failing in double shear here. So PS would be equal to N1 plus 1.875 N2 into pi by 4 dr square into tau here. So this is N1 value is 1 here, and this N2 value is 4 here. So we put all these value here, and then dr value is 24 whole square into 60. So from this expression we got the value of PS as 230.6016 kilonewton. The crushing strength per pitch length is, this is N1 plus N2 number of rivets into dr into T is the projected area basically of the rivet, and the thickness of the plate here, and the sigma C is the crushing stress. So N1 is 1 plus N2 value is 4, the net value here is 5 here, dr is 24, the thickness of the plate is 15 into sigma C is 120. So from here we got the value of PC as 216 kilonewton. The strength of the solid plate per pitch length is, that is P D into sigma T. Here in this expression we put the value of dr as 0. Okay, so we got a solid plate per pitch length. This is P D sigma T. We put all the value here. We got the value of the P solid for 156 kilonewton. Now out of these three values we have to see which value is least. So this tensile strength per pitch length, this PT value is least here. So least of this value is PT divided by P of the solid plate into 100. We put the value of PT here as 127.2 kilonewton, and by P solid, the strength of the solid plate is 156 kilonewton. We put here this 156 kilonewton. Okay, multiplied by 100 here. If we solve this expression, we got the value of 81.53 basically. So we assume the efficiency of the joint as 80%, but when we some dimension we have to modify it, some dimension we have to approximate. That's why the efficiency of the joint is changed here, and the new efficiency of the joint is 81.53. In this video we learned how to design a longitudinal boiler joint design. We have to see the step-by-step procedure with the help of an example and see how to find out the different values of the joints with the help of the formulas, and see how to round off these values and how to find out the efficiency at the last when we do when some dimension we have to modify something. If you like this video, please like, share, subscribe and comment.